Well, greetings, Mr. Kolazar's class. We're going to start introducing our new subject known as intermolecular forces. A lot of times this term intermolecular forces is going to be abbreviated IMF or IMFs, intermolecular forces. And what we're going to be looking at is different types of them, including LDFs, dipole-dipole, and hydrogen bonding, just to name kind of our three key ones, to look at different states of matter depending on the temperature that's given. So one question that we have to begin with is just this idea that temperature is the average kinetic energy of all the particles of matter there. Now, one idea is that if at room temperature, they all have the same kinetic energy. But a lot of times we have materials that are either solids, liquids, or gases, depending on what's going on room temperature wise. So there must be something beyond temperature that's causing things to be solids, liquids, or gases. So to begin with today, we're going to look at two factors that affect the state of matter. Our first factor that affects the state of matter is kinetic energy, energy of motion or temperature. So all things have kinetic energy. Higher temperature, remember, faster moving particles. Lower temperature, slower moving particles. Uh, Particles that are moved more tend to be further apart from one another. So as we're working, I would like to make sure we include our information below each infograph. First off, on your little slide here, make sure that you actually include one or two little gas particles moving around since they're not on your page when the animation was printed. Gas particles, fast moving, not touching, they just collide and bounce off on each other. So, they touch for that moment, but they just collide and keep bouncing in every direction, very fast moving. Liquids, touching each other, moving around in constant motion. So they're connected to each other, but they continue to slosh around each other. Solids locked in place, fixed position, they just vibrate back and forth. So they are moving, but they're just locked into that solid structure. So our first part of it is kinetic energy. Our second part is going to be the attractive forces within and between the particles. Our first one, intramolecular force, is within. They're very strong, and we either have ionic, covalent, or metallic. So remember, ionic is our metal plus the nonmetal, covalent, nonmetal, sharing of electrons, and metallic is just two metals combining together there. So they're either sharing, giving, or taking of electrons in order for that to happen. Very strong bonds. The other one we want to look at is the important one for our chapter is intermolecular forces. Intermolecular forces is given that abbreviation IMFs. So our intermolecular forces, forces that are between two molecules, are between molecules. So when we look at that, it's a force of attraction between one molecule and another molecule. It can be strong, but significantly weaker than intramolecular forces. And the three types we're going to look at, LDFs, dipole-dipole, and hydrogen bonding are the three we're going to be talking about. So our first one, LDFs. LDFs, known as London dispersion forces, are the weakest of the IMFs, result in a temporary shift in electron density of electrons in electron cloud. Can be strong when many are applied, but still very weak. Usually are non-polar molecules, such as CH4. I'd like to make sure we add in this note here and this note on the other side. So our first part is just a picture drawing. We've got this little sigma sign with a negative. That's our partial negative or partial positive symbols here. So on one side there's a partial negative, on another side there's a partial positive, showing that temporary shift in electron density. So as the electrons move around in that molecule, as they move around from one side, they become more negative, so the other side becomes more positive. There's a slight attractive force between the positive end of one side and the negative end of the other side. So there's that slight attractive force between those. Remember, these ones are temporary, because as the electrons move and shift back, then one side would become negative, now the other side would become negative, and the other side would be positive. So we'd have a different attractive force as it would go from negative to positive, and then to negative to positive. So as that shift happens between those, we get that attraction between those ones. Now, noble gases are usually non-polar. Like an example, noble gas, if you had like neon and neon, those two for noble gases would have almost no attraction between. And so since they have no attraction between them, there would be always gases. Until very, very low temperatures, those noble gases will actually turn into liquids. Helium is the element that has the lowest temperature to actually turn to a liquid, and those ones actually will never get to be solids as we're going there. So little attraction between those ones. London dispersion forces. Cool example of this is gecko's feet. Gecko's feet at the very bottom have these very small, like hair-like structures, and each one has little attractive forces that allows it to attract ever so slightly to another material. Just having one doesn't do anything, but having many, many, many allows a gecko's foot to actually attract and have it run across very smooth surfaces, up glass walls and ceilings, things like that. And another cool part is with that attraction, they actually never get dirty. So dust, dirt doesn't actually stick to them, but they're able to stick to other things. So it's kind of a neat for our option there. So London dispersion forces, that first one. Our second one is dipole-dipole. So dipole-dipole is our second one. And what we're looking at is it's between two polar molecules. Stronger attraction between permanently polar molecules. So the opposite charged sides there. So this time I'd like you to add in our little part here showing that permanent shift in electron density. So we have a permanent negative and a permanent positive side. And that negative wants to attract to the positive parts of another molecule. That negative wants to attract to the positives attract to other negatives. So we get that full positive negative attraction between polar molecules. So hydrochloric acid, HCl, is an example one that wants to stick together. They want to hold together more. So it's a stronger force of attraction between separate molecules. And our third one, hydrogen bonding. Hydrogen bonding, an example with hydrogen bonding, it's a type of dipole-dipole, so it's still a dipole-dipole, it's just more specific or a stronger one between very polar molecules. To do that, you need hydrogen from an atom bonded to fluorine, oxygen, or nitrogen. A lot of times we'll call them the FON or the fun atoms, fluorine, oxygen, nitrogen. It's the strongest IMF. It's not a true bond because it's not ionic, covalent, or metallic, but it's the strongest of our IMFs. So polar molecules, an example would be that hydrogen-oxygen bond. Hydrogen is directly bonded to one of our three elements, fluorine, oxygen, or nitrogen. The hydrogen-oxygen bond makes for a very negative part with the oxygen and a very positive part with the hydrogen. So that positive part wants to attract to the negative part of the oxygen. Positive here attracts to the negative. Positive here attracts to the negative of the next one. The positive to the negative. So we're getting that attractive force between hydrogen when it's bonded to an oxygen, fluorine, or nitrogen. So with our intermolecular forces, great place we see hydrogen bonding is hydrogen bonding occurs between our two strands of the DNA chain. So when DNA zips and unzips for coding and recoding or encoding of our information, we can see that C and G will always pair together, A and T always pair together. The reason why, if we were to look at that C and G and A and T, when adenine and thymine always connect, we've got a hydrogen bonding occurring and a hydrogen bonding, so two hydrogen bonds are formed between either oxygen and hydrogen or nitrogen and hydrogen, or on the other side, three C and G's make a three hydrogen bond between hydrogen, oxygen, or hydrogen and nitrogen in order for them to always match up completely together there. And so to end our section, we've got a little bit of writing on this last part. This is our key part, so you're going to have to write small for that one. States of matter, solids, strong attractive forces holding them together. Temperature, very weak energy. Just the opposite, very weak forces holding gases together, but a lot of energy from temperature causing motion and movement to play a factor. The liquids is in that weird in-between state where you're not solid, you're not gas, you're quite in between the two. Allows us to make and break, easily put back together, no forces holding together. IMF, strong physical bonds, easy to break, but generally when you break those, we can't put them back together unless it's a physical chemical change. This one's kind of key coming up in the next couple chapters once we get to solids. Besides that, everyone, safe travels and have a great day.